Hello and good time of day to you. Here's the main board from a Spectrum Plus 2, the type that should live in a grey case. I've been sent just the main board, nothing else, to save on postage costs, and its owner tells me it produces no video output. I've already had a quick look at the circuit board, and from the rear I noticed that 3 of the transistors have very obviously been replaced. These 2 over here have been left with their leads along, which clearly isn't appropriate in the long run, but they don't seem to be touching anything they shouldn't, so I will leave them for now. And this one over here has been replaced too, and a horrible mess has been made of the circuit board in the process, and there are now some little wire jumpers to repair tracks that were damaged. I want to start off by checking that these transistors that have been replaced are connected correctly. To do that, I've got a multimeter set to its continuity test mode. Let's start with transistor TR4. That's this one up here. The transistor installed is a 2N3904, which is what the circuit diagram shows it should be. It's this transistor here. The diagram shows its emitter is connected to one side of this 75 ohm resistor. There isn't a designator against that resistor, so it might be a little bit difficult to find that on the circuit board. Its collector is connected to the 12 volt supply, and its base is connected to one side of resistor R10 and to one side of diode D7. From the datasheet I know this transistor's center pin is its base, and from the way it's installed at the moment, its collector should be the pin on the left. So that's this one here, and that should be connected to the 12 volts power supply rail. Now I don't know immediately off the top of my head where to find that, but I know that the video encoder IC, this one here, has a 12 volt supply, so I'll run along its pins and we should find a connection. There we go, that one. So I think the collector of this transistor is probably correctly connected. Let's try and put this probe on its center pin, its base. And I can see labelled on the circuit board right next to it, there's a diode here, D7. So let's try the side of that. This side. So I think its base is correctly connected. And then obviously its other pin on the right hand side must be its emitter. And that connects to one side of a 75 ohm resistor. And I checked in advance to find out where that is, and on this particular version of the main board, that resistor is contained inside this package here. It's a network of resistors combined in one unit. So if I check its pins, there it is there. So I don't know whether or not transistor TR4 is damaged or working properly, however I think it is installed correctly. Let's move on to the other 2 that have been replaced. They are TR8 and TR9. The diagram shows that transistor TR8 up here should be a type ZTX213 and installed as a BC307, which I think should be an appropriate replacement. I'm sure we'll soon find out. Its emitter here should be connected to the 5 volt power supply and its collector to one side of resistor R29. I know from its datasheet that its center pin is its base, and as it's installed now, this leg here should be its emitter, and that should be connected to the 5 volt power supply line, which should be the right hand pin of the voltage regulator. So let's see whether that's true. Seems not to be. Let's try the other leg, which should be its collector. And that PCB pad there is connected to the 5 volt power supply line. So I think we'll find this transistor is installed the wrong way around. That means that its collector should be the terminal I first connected to, and that should connect to one side of resistor R29, which I think is this one up here. It's one side of it, and there's the other. Yes, that's correct. So transistor TR8 seems to be installed the wrong way around. There's one more to check, TR9, this one up here. The diagram says it should be a ZTX 650, and indeed that's what is installed. A good way to check this will be to confirm that its base is connected to one side of the inductor one of the windings of the inductor coil, and that its collector is connected to the other winding, and its emitter should be connected to the 0-volt power supply line. So again, its center pin is its base. So that's one winding of the inductor coil, and there's the other winding. So that's correct. And the way it's installed now, its collector should be its upper leg, and that should connect to the other inductor winding. It does. And finally, the emitter down here should connect to the 0-volt power supply rail, say the tab of the regulator. That's correct. So TR9 is installed correctly. I've removed TR8, here it is. I want to test it to see whether it's faulty, and also see whether I can check my interpretation of the pinout diagram on its datasheet, and therefore confirm that it was installed the wrong way around. Its center pin, its base, is connected to the negative lead of this multimeter, which is set to its diode test mode, and with the way it's mounted, the right-hand terminal is its emitter and the left-hand one its collector. The base emitter and base collector junctions should both conduct when forward biased, which is what I'm about to do with the multimeter, and it might be possible to tell which is the base collector junction and which is the base emitter junction. Typically, the forward voltage across the base collector junction is slightly lower than across the base emitter junction, because the base collector junction is usually larger. Now, it's often very difficult to tell with small transistors like this. The effect is much more noticeable with larger power transistors. But let's have a go. So again, on the right hand side should be its emitter, and the forward voltage drop across that junction is 673 millivolts. And now if I try the base collector junction, 669 millivolts. So that's very slightly lower, and does suggest that both this transistor is working and that my interpretation of its pinout is correct. So I'm going to reinstall it, but the proper way around. I've connected the computer up to a bench power supply and the RF video output to a television. I've mounted the voltage regulator on a temporary heatsink, so I'll be able to have it turned on for more than a few seconds without that component being damaged. I've also got a multimeter to hand to measure power supply voltages if appropriate. Let's switch it on and see what happens. Excellent. It seems the only major fault then was the incorrect installation of transistor TR8, and that would produce a symptom of no video signal in the +2, because the TEA 2000 video encoder requires the 12-volt supply produced by the voltage converter circuit. Now this computer's working, I thought it could be helpful to have a look at some other common problems that affect the +2, and also to examine the options for the different video signals that can be presented on this DIN connector at the rear, as there are a number of possibilities and it can be a bit confusing. From some notes I made when I worked on another +2 a while ago, I noted that there were 3 transistors that are quite often installed the wrong way around at the factory when these were manufactured. One of them was TR4 back here. We've already looked at that one, and it's been replaced and is now the correct way around. The other 2 were TR5, this one over here, and TR7. So I want to check to see whether those are installed the correct way around in this example. I'll start with TR5 over here. Look at the circuit diagram. It's this transistor here, and it acts as a buffer in the delivery of the TTL vertical sync signal, which is one of the video options that can be presented on the rear socket. If that's not installed the right way around, then that signal can never be present. So like before, I'll use a multimeter on its continuity test mode, and from the circuit diagram I can see that this transistor's collector should be connected to the 5-volt power supply rail. That's probably a very easy thing to test for. And with the way this transistor is installed, it's a 2N3904. Then its collector is its right hand leg, this one here. And it seems not to be connected to the 5-volt power supply rail. I expect its left hand terminal will be. It is. So that shows that transistor is installed the wrong way around. And the other one to check is this one, TR7. This one's a bit more curious. It's this transistor here, and its job is to pull the ULA's IO request line high whenever address line A0 is high. Now that was necessary because of a design bug in the ULA, and without it, it means that the ULA detects memory contention in some situations when it shouldn't do, and suspends the CPU. Now I don't know whether or not this particular bug was corrected in the ULA for the +2. If it was, then this transistor is not necessary, and it being installed the wrong way around doesn't matter at all. If it is necessary, then it being installed the wrong way around means that the timing of the +2 isn't as it should be, in that the ULA suspends the CPU at some times when it doesn't need to. However, on a previous +2 where I found this transistor installed incorrectly, I turned it around and certainly it had no ill effect. So if this one is installed the wrong way around, I propose correcting that too, but I'm really not sure whether or not it's necessary. So again, this transistor has a connection to the 5-volt power supply line. That should be easy to check for, and its collector, and it's another 2N3904. So given the way this transistor is installed, its collector should be the upper lead there. Now it doesn't seem to be connected to the 5-volt power supply. Let's see whether the pad at its lower lead is. It is, so yes, that transistor is also installed the wrong way around. I've reinstalled those transistors the correct way around. You might have noticed that the silkscreen marking on this circuit board is incorrect for the orientation of the transistors installed here. I know that different transistors were used in some +2s, so perhaps those markings are correct for those types. I've confirmed the computer is still working, and I've also done my best to repair the circuit board damage where transistor TR4 is mounted. All three of the pads where this transistor is fitted have been torn away from the board. I always feel a bit sad when I see something like this has happened. So if you're considering working on or repairing a piece of equipment like this, or anything that's important to you or could be considered a historical item, and if you're not confident you can do it without causing any damage, then practice on some junk equipment first, or perhaps assemble some cheap electronics kits to get some experience. With a bit of practice, it isn't at all difficult to remove a transistor without causing damage like this. As promised, let's have a look at the signals that can be presented at the video connector on the rear of the grey-cased +2. In this diagram, these numbered lines represent the pins of the DIN connector. The note suggests there are two possible configurations, called standard and peritel, another name for the SCART standard. The signal present on some of the pins depends on which wire jumper links are present and whether certain components are installed. In standard configuration, composite video is present on pin 1. In this case, link 4 is fitted and link 2 not. This signal is buffered by transistor TR4. This is one of the transistors that is often installed the wrong way around, and so this must be corrected if a composite video output is wanted. In the peritel setting, pin 1 carries 12 volts. This might be useful for controlling the settings of a device with a SCART input. Pin 2 is always connected to the 0-volt power supply rail. Pins 6, 7 and 8 supply the separate red, green and blue video signals. In the standard configuration, these use TTL digital voltage levels. Resistors R12 to R14 and their series diodes are not present. It will be appropriate to connect these to a monitor that has TTL RGB inputs. The monitor must also have a separate TTL brightness input if it is to display all of the spectrum's colors. Otherwise, only 8 will be possible, and the normal and bright variations of each color will appear the same. In the peritel configuration, these resistors and diodes are present, and they combine the RGB signals with the brightness signal to produce output suitable for connecting to a display with an analog RGB input, such as a television SCART socket. Pin 4 always carries the composite synchronization signal as generated by the ULA. Pin 5 supplies a vertical synchronization signal in standard mode. In this case, link 1 is fitted and link 3 not. The vertical sync signal is separated from the composite sync by this simple filter circuit. It includes transistor TR5, and this is another that is often installed incorrectly, and if so, it must be refitted if a vertical sync output is required. In peritel mode, pin 5 carries 12 volts, just like pin 1. Finally, if link 7 is installed for standard mode, pin 3 carries the TTL brightness signal referred to earlier. At any particular instance, it indicates whether the color being displayed should be at normal or extra brightness. If link 8 is installed instead for peritel mode, then pin 3 provides the spectrum's audio output. It is exactly the same as available from the separate audio connector. I found that most commonly the outputs are configured as I've just described for standard mode, apart from the RGB signals, which are set up in the peritel configuration. This is reasonably useful, as it means the video output can directly drive a television with a SCART input. If you want to use the video output DIN connector, you should check exactly what signals your display requires and see how the +2 is configured. It might be necessary to change some links, or remove the resistors or diodes. Removing just one or the other will do, if you need a TTL RGB output. You might also need to refit some of the transistors. I've always found the blue and yellow ghosting effect around graphics on the 128K models of Spectrum rather annoying. Please excuse any flickering here, it's just because I'm pointing a camera at a television set. This ghosting effect is present whenever the composite video output is used, whether that's via the RF modulator or the DIN connector. This led me to having a closer look at how the TA2000 IC is used in the Spectrum. Here's part of the +2 circuit diagram. Unlike earlier models of Spectrum, the ULA generates RGB outputs. The TA2000 takes a 6-bit binary input and from this generates a composite video signal. After reading its datasheet, my attention was drawn to this filter network down here. The datasheet describes that as an optional chrominance filter, and it doesn't say much about why it might be necessary. However, it does say that using it will introduce a slight delay in the chroma signal, and so if this filter is used, it's also necessary to add a delay line component to the luminance signal so that the two will match up again. And certainly if the chroma and luma signals are not coincident in time, then that would cause a ghosting effect. The luminance signal is output on pin 7 here, and in this case is fed via a simple resistor divider network back to pin 8. There's certainly nothing there to introduce a delay. Now the inductor in this filter network is adjustable, and varying its value does affect the severity of the ghosting, but it's not possible to get rid of it. On this particular +2, I think the threads of that inductor's core are slightly damaged because I found it very difficult to adjust, but by temporarily gluing a small plastic tube to it, I was able to move it to a position to minimize the ghosting, but it's still present and rather annoying. The datasheet says this filter is entirely optional, so I've tried disconnecting it altogether by removing this capacitor here, C3. However, that didn't make much difference at all. I've also read, I think in a post on the World of Spectrum forums, that this ghosting effect is primarily due to high frequency interference on the luminance signal, so that's something I want to investigate further. I've coupled the luminance signal at pin 8 of the TA2000 to this spectrum analyzer. The central vertical line represents 4 MHz, and the horizontal scale is set such that each major square represents 500 kHz. The picture information contained in the luminance signal should be towards the left-hand side. Colour information will be added to this later inside the TA2000 by modulating a 4.43 MHz carrier to generate the chroma signal. This means that we'd hope that the area around 4.43 MHz on this spectral plot shouldn't contain any information. However, it does, and if that makes it through to the television, then it'll be wrongly interpreted as colour information. That could well be what's causing the ghosting effect. I'd like to try adding a filter to remove signals around about 4.43 MHz to see whether that improves the situation. However, I can't use a simple, for example, low-pass filter, because look over on the right-hand side, at exactly 6 MHz is the audio carrier. This must remain if the television is to receive the spectrum's audio output. As an aside, while experimenting, I noticed that the spectrum sets the central area of its display to black for a moment while it's initializing, and so during that time there's not very much luminance information. You can see that here if I briefly press the reset switch. I'll do it a few times. If you look closely, you might notice that during that period there's still a small peak at just over 3.5 MHz. I suspect that's the CPU's clock being coupled into the signal I've linked to the spectrum analyzer. I propose connecting a series LC circuit like this one to pin 8 of the TA2000. This circuit has a low impedance close to some particular resonant frequency and a higher impedance at other frequencies. This can be used to remove signals close to 4.4 MHz from the Luma signal. This equation is used to calculate the resonant frequency, which we already know needs to be about 4.4 MHz, and the only physically small inductors I've got on hand are 15 microhenries. So if I put those figures into the equation and rearrange it, I end up with a value of 87 picofarads for the required capacitor. I've got some 100 picofarad ceramic disc capacitors, one of those would probably do, but I'm going to go with a 68 and a 22 picofarad capacitor in parallel to give 90 picofarads. Here's the filter soldered directly to the pins of the video encoder IC. Here's the spectral plot of the signal on pin 8 of the TA2000 now. An enormous difference isn't immediately apparent. However, the strength of signals around 4.5 MHz is certainly slightly reduced, and the audio carrier at 6 MHz is unaffected. My rather ad hoc method of connecting the spectrum analyzer to the computer is certainly not helping either. I've used some flying leads with crocodile clips to add a DC blocking capacitor and a resistor to prevent the spectrum analyzer's input from overloading the signal. This will certainly be picking up a great deal of additional interference. I also suspect the bandwidth of the filter isn't quite as wide as ideally it should be. The easiest way to increase this would be to add some series resistance to the filter, However, this would also reduce the attenuation at the resonant frequency. I don't think I'll bother making any further modifications though, because if I disconnect the spectrum analyzer, here's the picture on the television now. The ghost effect, while still present, is enormously reduced and isn't particularly annoying at all. And here's the picture if I use the composite video output from this +2. The ghosting has pretty much disappeared altogether, and I don't think I've ever seen such a good, clear picture from a +2 from its composite video output before. There's another modification I've sometimes previously made to +2 spectrums that can slightly improve the quality of the picture when the composite video output is used. That's the one present on pin 1 at the DIN connector. The potential problem is that this signal includes the modulated 6 MHz audio carrier. Now, most televisions and monitors won't be designed to expect this signal to be present. It doesn't normally cause a problem, but if the display doesn't do a good job of filtering it out, or perhaps has some nonlinearities in its input circuitry, then distortion products of this carrier could affect the picture. This IC here, IC11, generates the modulated audio carrier, and it's coupled by this 20 picofarad capacitor C31 up to pin 8 of the TEA2000. This adds the audio carrier to the luminance signal, and it passes straight through the TEA2000 and appears on its composite video output at pin 6. This is then fed via these buffer transistors to the RF modulator and to the composite video output at pin 1 of the DIN socket. We would like the audio signal to continue to be present on the RF modulated output so that an ordinary television set will receive it, but there's no need for it to be present on the composite output at the DIN connector. So the modification I've made before is to remove this capacitor C31 and instead connect a 20 picofarad capacitor from pin 4 of IC11 up to the emitter of transistor TR2. This will add the audio carrier to the composite signal that goes to the RF modulator, but it will no longer be present on the composite output at the DIN connector. Capacitor C31 is this small one in here, although I've noticed that on a few +2s it seems to have been omitted at manufacture and was added as an afterthought and is soldered on the rear of the circuit board. It's a fairly simple procedure to remove this capacitor and to connect a new one from the appropriate pad here over to the emitter of transistor TR2, which is nearby. Here's C31's replacement, coupling the audio carrier to TR2's emitter. I've temporarily connected a keyboard so I can hold down the brake key while starting the spectrum. This makes it go into its display test mode, and you can see that here. The television is connected via the spectrum's RF modulator output. If I turn up the television's volume control, we can hear the test tone. This is clear proof the audio carrier is present on the signal output from the RF modulator. But let's now prove that it's no longer present on the composite output. First, I've connected the output of the +2's RF modulator to the spectrum analyzer. I've turned on averaging so we get a more stable display. UHF television channel 36 is at around about 591 MHz, and I found the luminance carrier here at 591.5. It's represented by the large peak in the centre of the display. We can ignore everything to its left, as I believe in a broadcast television system these sidebands wouldn't be present, but the spectrum's modulator hasn't bothered to filter them out. That shouldn't cause any problems. Immediately to the right of the central peak are the varying modulation components caused by modulating the carrier with whatever is being displayed at the time the analyzer carried out its sweep. Offset to the right by 4.4 MHz, there's a peak that comes and goes. That's due to the chroma subcarrier. Now the chroma subcarrier isn't transmitted or as part of the television signal other than briefly during the colour burst. However, clearly the colour burst is going to occur sometimes while the analyzer is performing its sweep, and so we can see the peak here. And then a bit further to its right is a signal offset from the Luma carrier by 6 MHz, and that's the sound carrier. I can prove that by centering the display on that signal. And then reducing the scan width down to 0, because this spectrum analyzer incorporates a receiver for its intermediate frequency, and that will demodulate the signal and allow us to hear it. There's the test tone from the spectrum. Now I'll reconnect the spectrum analyzer's input to the composite video output from the spectrum. This time there's no modulated luminance carrier, so I'll adjust the center frequency of the analyzer to 4 MHz. I'll turn off averaging. And what we can see there are the frequency components of the composite video output. However, the important thing to note here is that there is no audio carrier. If there was, we would see it at 6 MHz, which on this scale would be offset by 4 squares to the right of the center line.